Rajiv sir.
Huh.
Okay.
Am I audible?
Yes, yes.
Yes,
Okay.
sir. Yes, sir.
Okay.
Noble, shall we start?
Yeah, please.
Yagumare,
Yeah, sir. Tell me.
shall we start?
Of course, sir.
Good evening. Welcome to today's session of 6-day faculty development program on recent research advances in geotechnical and geological engineering at Rajagiri School of Engineering and Technology, Kochi. Today's session will be handled by Dr. Noble Jacob. Welcome, Noble Jacob. Dr. Noble Jacob is
Thanks.
presently working as a senior scientist at Isotope Hydrology Section, Baba Atomic Research Center, Mumbai. He graduated in civil engineering from Government Engineering College, now Government Rajiv Gandhi Institute of Technology, Kottayam, Kerala, and had master's degree in water resources engineering from NIT Warangal, and further did PhD in water resource engineering from IIT Bombay, Mumbai. He was awarded the British Council's Commonwealth Professional Fellowship in 2007 and did postdoctoral research at University of Oxford, UK. Also, he was awarded the Center for International Cooperation and Development Fellowship in 2009 and did advanced research at University of Pavia, Italy. He has 23 years of research experience on the application on environmental and artificial isotopes in hydrological investigation in conjunction with conventional hydrology, hydrogeology, hydrochemistry, and numerical modeling. His research interests include recharge and dynamics of groundwater, surface water, groundwater interactions, river flows, lake hydrology, effect of climate change on water resources in snow or glacier-dominated regions, estimation of submarine groundwater discharge in coastal regions, groundwater pollution, fingerprinting of seepage sources in dams, reservoirs, and tunnels, pollutant dispersion and sediment transport in estuaries and coastal areas, etc. He has served as an International Atomic Energy Agency expert in 2016 to study groundwater issues of Kuwait. He is a permanent reviewer of some of the topmost journals in hydrology and hydrogeology and reviewed more than 100 articles. He has published more than 50 papers in high impact factor international journals. We welcome you, Dr. Noble Jacob. Now over to Dr. Noble Jacob for his session.
Thank you, Professor Rajiv Kumar, for the nice words of introduction, and welcome you all for today's presentation. Today's topic is tracer techniques for studying subsurface flow problems. As you all know that as a civil engineers, we look at the subsurface problems based on theoretical calculations or by lab experiments. But many times the field problems are quite different from what we pursue. Hence, tracer techniques are a sort of new technology wherein we work on the actual field problems. Now, coming to the flow in the subsurface, we all think that the flow of groundwater is just the flow through porous media. That's not correct, because the geology is different at different places. Hence, the flow pattern and the flow is different in different geological settings. The flow can be classified into 4 types. First one we all know is the flow through porous media. That's the flow through the alluvial sandy aquifer system. You can see a schematic picture of the sandy aquifer system. Now, next comes the flow through the weathered zone. Because the parent rock, if it is a hard rock like granite, it undergoes weathering, chemical or physical, and the sediment get weathered, and the flow in that weathered sediments are different. For example, it is laterite is a weathered component of the granitic rocks. Now, third comes the fractured flow. That is in the case of hard rock like granite, where there are so much, as you see the third picture here, it consists of a lot of fractures, interconnected joints. The flow in that case is quite different from the other two flows. And third comes the flow through limestone aquifers. In the case of carbonate or limestone aquifers, because of the rock water interaction, solution channels are produced in the subsurface, and the flow is just like a channel flow in the carbonate aquifers. So please visualize that the flow in the subsurface are different with respect to the geology of the area. Hence, simple calculation, mathematical calculations or theoretical consideration will not help to solve actual problems. In this case, tracers can be used to understand the real actual world problems, subsurface geological problems. Now, what is a tracer? Tracer is nothing but some particles which is part of the system, but at the same time, it is having some properties which enable us to detect it. For example, suppose there is a big group of people there, and if you want to trace one person, that person should have a particular colored shirt. If he moves, you can see from different area, different place. The same way, tracer is also like the system, but it is having a different property which enable us for detection. Now, how to select a tracer? The selection of tracer depends upon the problem which you are going to study. If you are going to study the water, then you need to look for some water soluble traces. If you are looking at the sediments, then you look for some sediment traces. So like that, depending upon the properties. Now, one of the main advantages, need of the tracer is that you should have high detection sensitivity. Suppose you all know that we inject some dye tracers in some places and we monitor at some place, some other places. Now the issue with the dye tracer is that once it is diluted, you cannot see it, you cannot measure it. So always your tracer should have good detection sensitivity even after dilution, especially in the subsurface. The flows, the volume of water is very high, dilutions are quite high. So even after dilutions, one would be able to trace, detect it at different places. Now, tracer methods can be classified into two. One is the environmental traces, and second is the artificial traces. Environmental traces mean the tracer is already there in the nature. You need not have to inject anything there. You have to just collect a sample and measure the concentration. And based on the concentration, and the history of that tracer, you can calculate what are the process happening. In the case of environmental traces, it gives regional picture, large spatial and temporal scale pictures you get. But whereas in the case of artificial traces, which you inject at a one point and you monitor it at another point, it gives site specific information. Now, coming to the different classification of environmental traces, it can be chemical traces and traces like isotopes. Now, as I said, environmental traces mean it is naturally present. It is already present in the atmosphere. So in the subsurface, you have to just collect the sample and measure it. That's all. See, for example, the chemical tracer can be natural. Chemical tracer can be the electric conductivity of water, or the chloride, whatever be the thing, or the isotopes of water, because water mean it is hydrogen and oxygen. H2O is water. So the isotopes of hydrogen and isotopes of oxygen or any other chemicals which is dissolved in water, if you can measure it, that could be can help you to trace the path of the water molecule which has come from the different places. Now, you all know what is an isotope. I will explain in the next slide what is an isotope. Isotopes are classified into two: stable isotopes and radioactive isotopes. The isotopes which undergo radioactive decay is called radioisotope, which changes with time. The activity changes with time. But whereas stable isotope mean isotope which is not changing with respect to time. Now, the most commonly used water traces are the deuterium, that is 2H, and the oxygen 18, because hydrogen and oxygen forms the part of the water molecule. Now, for pollution studies, especially nitrate pollution, sulfate pollution, or if you want to see the industrial pollution, sewage pollution, then N15, sulfur 34, boron 11, these natural isotopes can be measured, and that will help you to understand the pollution problem. In the case of sediments, lead 210 can help. And now coming to the radioactive environmental isotopes, tritium and carbon 14, 3H and carbon 14, they are used to find out the residence time of water, the age of water, and some dissolved gases like radon and dissolved solids like radium can be also be studied to find out the residence time of groundwater. Now, cesium-137 is a radioactive isotope which is used to study the sediments. So, the isotope so far I was talking about were naturally present. Now, coming to the injected traces, we can be classified into two. One is chemical traces, and another one is the isotope-based traces. Chemical traces, mostly we are all familiar. That is, either you inject chloride or bromide for groundwater velocity measurements and things like that, or you can use dye traces like rhodomen WT and things like that. Now, the second classification about isotope-based traces, artificial traces, which is nuclear reactor-produced isotopes, which we produce in the nuclear reactor, take it to the site, inject at one point, and then monitor at different places. For studying the water problem, mostly bromine 82, which is a water-soluble tracer, or iodine 131, or tritium 3H is used. For studying the sediments, we artificially produce glasses in the form of scandium 46, or gold 198. These are the sediment traces. And if you want to study the petroleum oil movement, we use carbon 14 in the form of methyl alcohol. So these are some of the broad view of the environmental as well as injected traces available to us. Now, coming to simple basic concepts of atoms, you know that all molecules, say water or any other molecule, is made up of atoms. And in an atom, you have a proton and neutron at the center of that is called the nucleus, and electrons around it. And the total number of proton and neutron give the weight of the atom, that is the mass. So always this mass is at the center of the nucleus. So now, what is an isotope? Isotope is nothing but atoms which is having different masses. Because of the difference in number of neutrons, the masses of different isotopes changes. Isotopes can be broadly classified into stable isotopes, which do not undergo any change, and radioactive isotopes, which undergo changes, which emit radiations like alpha, beta, gamma, and undergoes and changes to another isotope. Now, coming to the isotopes of our interest, if you are studying the water, water is made up of hydrogen and oxygen. So the hydrogen has three isotopes. H1, that is called the protium, H2 is the deuterium, and 3H is the tritium. Now, tritium is the radioactive isotope, whereas hydrogen and protium and deuterium are stable isotopes. Now, coming to the masses, the superscript, if you see, the protium is having one neutron, one proton. That's why it is 1. But whereas the deuterium, the mass is 2. So the deuterium has double the mass of the protium. So that's what it means. So different isotopes have different masses. Although we consider hydrogen as a single element, but hydrogen has many isotopes, and they are different in masses. Their masses are different. The same case with the oxygen and carbon. In carbon is normally dissolved in water. So that dissolved carbon in the form of carbon-14, which is a radioactive isotope, which can be used to find out the age of groundwater. Now, coming to the stable isotopes, as I said, the most commonly common isotope of hydrogen is the protium, that is the H1, which is 99.9% is that one. But whereas the deuterium, the percentage of deuterium is very low, 0.01% only, although its mass is different. Now, what we do, water can be, even though we say H2O, it can be 1H, 1H O16 or 1H, 2H O16 or 1H, 1H O18. So different isotopes of water, combination of water is possible. Now, if you use water isotopes for understanding the subsurface processes, we measure the most common isotope, that is the 1H, by the rare isotopes, that is given by isotope ratio. Isotope ratio is given by the abundance of the rare isotope, that is the 2H divided by the abundance of the most common isotope. So this ratio is called 2H by 1H ratio is called isotope ratio. And that value is very small because we are looking at the atoms. So always that is measured with respect to a standard. Standard is the mean sea ocean water. Why? Because the hydrological cycle starts from the ocean. So that is considered as the standard, which is having a value of 0 isotopic content. Now, with respect to seawater, how the groundwater, river water, lake water changes. That's what we really look at. And that is expressed in terms of delta form symbol, that is per mil. Per mil is parts per thousand. Instead of we express in terms of percentages. And here isotopes are measured, expressed in terms of parts per thousand. That is, it is called per mil. So, so once you collect a sample, measure its stable isotopes, that will help you to understand the flow processes. Now, coming to these stable isotopes, during physical and chemical processes, there is a change in these ratios. Because, say, for example, the heavier masses, in the case of an evaporation process, if a water is evaporating, then the vapor contains more lighter particle, that is 1H is more in the vapor phase, but the 2H is less in the vapor phase. Why? Because, see, for example, I'll tell you an example. See, if a fat person, a heavy person and a lean person, a low weight person are going for a race, who will win the race? Obviously the lean person, because his weight is less. The same way, in the case of any physical or chemical process, the different isotope behaves differently. The heavier one will remain in the liquid phase, whereas the lighter one will go into the vapor phase. So in that case, different water, whether it's a precipitation sample or it's a groundwater or river water, they will have different values because of the physical and chemical processes. Now, this is the isotopes which are, as I said, the radioactive isotopes are used to find out the age of groundwater. Tritium is a isotope which is used to find out the age of groundwater. It can date the ages of for the last 50 years because his half-life is 12.43 years. So it can date up to last 50 years, water, finding the ages of water which are recharged during the 50 years. But whereas carbon-14 is having a half-life of 5,730 years. So it can date the groundwater up to 30,000 years. And if the water is still older, we use chlorine-36, which can date even thousands and, millions of years. So these are the three isotopes which we use for finding out the age of groundwater. Now, this is the instrumentation which we use it. This is the mass spectrometer called. This is used for the measurement of stable isotopes like deuterium, oxygen-18, carbon-13, and things like that. But whereas this is a liquid scintillation counter, which is a beta counter, and this is used for measuring the isotopes like tritium, carbon-14. So this is the very basics of the isotopes. Now, coming to the application, which you will be more interested. Mostly the environmental isotope, that is the environmental stable and radioactive isotope. Mostly the deuterium, oxygen-18, and tritium and carbon-14. They are normally used to study the following problems. See, for example, if you measure the isotopes, stable isotope precipitation, the rainwater, we can find from where the rain comes from. See, for example, recently in Kerala, there was a heavy rain last month. So if you measure the, collect the rainwater sample and measure it, we can tell why that much heavy rainfall come, whether it's coming from the Arabian Sea, which part of the Arabian Sea, what is the condition, the climatic condition present at the time of evaporation of the seawater, sea surface temperature. All these things can be traced out if you just collect a rainwater sample and measure its isotopes. The same way, now coming to the groundwater studies. As you all know, groundwater is recharged at some places in the shallow aquifers, and in the deeper confined aquifers, it is recharged hundreds of kilometers away, and it moves in the subsurface at a very slow rate. So now in the case of groundwater studies, you are asked to know two questions. First is from where this groundwater comes from. If I have a well, if I collect a water, I want to know from where this water comes from. That is called the source and origin of groundwater. Source means whether this groundwater comes from a river or from the rain or from a lake. That is a source, and origin is at what altitude it is recharged. So stable isotopes can find out what is the source and origin of groundwater. And dating of groundwater, there is finding out the ages, we can do that. Then surface water groundwater interaction, whether lake groundwater, whether the groundwater is contributing to a lake or lake is contributing to the groundwater. Surface river, how the river flows takes place, all these things can be studied. Aquifer interconnection, suppose you have a shallow aquifer, you have a deeper aquifer, whether they are connected or they are laterally flowing, all these things can be studied. Then origin of geothermal waters, because you are very much interested in the geothermal energy, the hot water springs. So from they originate, what is the temperature in the reservoir, all these things can be calculated. Then nowadays, rainwater harvesting, people are doing, how effective this rainwater harvesting in recharging the aquifers, that can be studied. Then stream flow generation process, because many times the river is sustained by many components, like sometimes the surface runoff, sometimes with the groundwater component in the hilly terrain, in the mountainous regions, in the Himalayan region. Sometimes glacier is a major component, snow is a component. So these components can be estimated if you just simply measure the isotopes of river. We can quantify it. Then groundwater pollution can be studied, whether it is a salinity pollution problem or it is a nitrate problem, that can be studied. Then salinization mechanisms can be studied. The groundwater discharge into the sea can be studied. Then environmental isotopes can be used to study the dynamics and the sedimentation rates of lakes. Especially nowadays, lakes are getting sediment. A lot of sediments are coming and their lives are decreasing. So sedimentation rates can be estimated using isotopes. Now coming to the artificial isotope, where we inject the isotope and then we monitor it. We can we can use these isotopes to find out the groundwater velocity and the direction of flow, and estimating the recharge, how much is the recharge happening, and if there is a irrigation return flow, if you are doing some irrigation, how much water is joining the groundwater, that can be studied. And now another problem is the seepage of canals, which we civil engineers are more interested in. Seepage of many canals, that can be estimated using isotopes. Then flow measurements in canals can be done. In the case of mountainous rivers, the river discharges can be calculated. And then another important study is the leakage through dams and reservoirs, because Mullaperiyar Dam and similar lot of leakage problems in the dams, which can be studied by injecting some tracers into that and monitor it. Then pollution dispersion in surface waters, because how the pollutants are dispersed, what is the dilution factor, how much is the dispersion coefficients, how well the surface waters are mixing. So those things can be calculated. And also sediment transport in ports and harbors, how the erosion takes place in a coastal region. So entire water resources region, conventional techniques which we study as civil engineers can be studied using isotope techniques. So this is the most, I covered the most of the application. Now coming to some of the case studies which you will be more interested in. And the first study is on the hydrodynamics of deep aquifers in South Kerala sedimentary basin. I am presenting some of the studies in Kerala, which you people are more interested in. So South Kerala sedimentary basin you all know that Kerala basically from Kollam to Cochin, the coastal belt have a thick sediments. Even see, this is a cross section of the here is a Cochin and here is the Kollam, and you see that the sediment, this is a sedimentary basin, mostly sediments are there, and even the sediment thickness goes more than 700 meters. Now there are different formation. This formation, this is a top formation. You have the shallow aquifer system. Below that there is a sandy aquifer system called the Varkala formation. That's commonly called as a Varkala formation because it is exposed in the place called Varkala. Now, this water, the Varkala formation, is mainly used for the drinking water supply of Alapi region. Most of the tube wells are tapping it. Now, we want to know from where this water comes from. Are they getting recharge? What is the recharge source? What is the history of the recharge? And what is the recharge area? And is there any connection between shallow aquifers and deeper aquifers? Is any vertical recharges? And the source and mechanism of groundwater contamination? Because this is a coastal aquifer in the Varkala formation, there are some salinity issues and there are some problem with the fluoride. So these are the problems to be addressed. So how isotopes can help in solving this problem, that I will tell you in the next slide. Now, this is we have collected the samples from the top shallow aquifers, the Varkala, the deeper aquifers, the Vemenad Lagoon, surface water, all samples we have collected. We measured for the oxygenating, that is in the x-axis, and the deuterium. Two isotopes we have measured, and it is plotted. Now, I'll tell you what this plot means. See, this is called the local meteoric. This black line is called the local meteoric line. That means that the precipitation which falls all over the world, the rainwater which falls all over the world will fall on this line, which is having a slope of about 8 and a y-intercept of about 10. So all the precipitation samples fall here. Now you see here again we have some precipitation. See, this is the precipitation sample. It is falling somewhere near here. Now the shallow aquifers, they are falling in a group of this black one. These are the shallow aquifers. But whereas the deeper one, our industry is the Varkala aquifer. This one, the open red circle one, these ones, they are falling in a different region. That means that they are isotopically they are different. That means that these modern shallow aquifers are not connected with the deeper ones. They are different because the isotopes changes only when there is a change in climate. So these waters, because they are slightly higher enriched value, that means higher isotopic values compared to the shallow aquifers. So that's why we can say that they are different. Now we have did some carbon 14 dating of this groundwater, and we found that most of these waters are modern water, but whereas the deeper waters, they are old waters. They have groundwater ages from 5,000 years to almost 30,000 years. That's what we have found out using carbon 14. So using the stable isotope and carbon 14, we could identify they are not shallow aquifers are not recharging vertically to the deeper aquifers, and the deeper aquifers are very old water and the dynamics are very slow. Now coming to the spatial distribution of the Varkala aquifer, see, this is the electric conductivity of the deeper aquifer, Varkala aquifers. You see that here some salinity, electric conductivities are higher, but whereas this is lower. Now this is the carbon 13 of say stable isotopic isotope of water. And you see that the pattern. See, normally we all know that this is the Western Ghats and this is Arabian Sea. The aquifer get recharged in the Western Ghats. It flows and goes into the sea. But if you see the flow pattern of this isotope, you see that instead of it is going into the sea from this region, it's a Kottayam somewhere here, Pandalam, Chenganur, this region, water is going into the Alapi region. So this is the flow pattern. So this flow pattern could be identified based on the isotopes. Now this is the plot which shows the residence time of water, the groundwater ages. See, these values, this 28 means it is 28,000, but whereas this 9 means 9,000. So that means that this is the recharge area. This Pandalam Chenganur region is the recharge area where the groundwater recharges into the aquifers and it flows, and as the water flows from here and reaches the Alapi, it will take some 20,000 years. So that's the information which we got from isotopes. Now coming to, from based on the carbon-14 ages, we have calculated the groundwater velocity. It is about 5 meter per year. That's the velocity. Now coming to the salinity here, now we found that based on isotopes, which I will explain in another slide, that this is not, although it is very close to the sea, it is not the salinity, saline seawater intrusion, but because these waters are old, so it is not connected with the sea directly, but this is due to the salts coming from the clay formation, and some places it is a trapped seawater. Now coming to the fluoride, because the fluoride which is comes, normally people expect that it comes from some industries, but whereas these waters are very old waters, and they are we found that this fluoride is coming from leaching of fluoride from the formation, from the rock, due to the long residence time. Now coming to another simple interesting study, wherein mining activities are happening. It's a study to understand the impact of iron ore mining in Goa. See here, mining activities are going on, and there was a public outcry that the mining activities causing contamination and health issues to the groundwater people who are using that. So the objective was to understand whether they are hydraulically connected or not, whether the mine pits are connected with the aquifers or not. So this is the oxygenating delta D plot where we collected the samples. We found that the mine pit waters are falling here, and whereas the groundwaters are falling here. That means that the mine waters, because they are evaporated, they are open water body, they are evaporated, hence they are enriched. But whereas the groundwater is the precipitation water that is falling in the global meteoric line. Now they are different. That's why this mine water is not contributing to the groundwater. Suppose if this mine water is contributing to the groundwater, then this groundwater samples should have been placed somewhere here, or a mixing line between these two. So this is the information which we got from isotopes. Now, as I said earlier, we can study the geothermal waters, how the hot water springs occurs. There are almost 18 hot water springs in Maharashtra, and this Thermax Pune is now looking for the exploration of exploitation of this hot water for power generation. And we did some studies to identify from where this water comes from, how it is getting the temperature, and what is the rock water interaction, and how the mixing of any water takes place or not. And our studies found that hot waters are not recently recharged water. They are old waters which are recharged somewhere and going in deep into the geological formation and comes out by convection. Now, significant interaction is taking place due to rock water interaction, and the temperature we estimated to be 140 to 160 degree. That is the temperature in the reservoir, and the mantle is the heating source. So this is a study information which we got from geothermal studies. Now, another interesting study is application of injected tracers is to find out the groundwater velocity in a well. If you want to know the groundwater velocity in deeper wells, shallow wells, anywhere, you can use. There are two methods normally followed. One is the point dilution technique, that is a single well method, and there is another method called the multiple well method. In single well method, as the title suggests, you have a single well. You inject the tracer here, mix it properly, then you measure the concentration changes with respect to depth. At different depths, you measure it at different times. So this is the single well. You inject the isotope or a tracer, dye trace, anything you inject, mix it properly, and you do the vertical. These are the vertical profiles at different times. You see that this is the concentration. The shallow, the top up to this level, there is a change in concentration. There is a decrease in concentration, whereas in the deeper ones, the concentrations are higher. That means that there is a flow in these only up to this place. So there is a flow, and the change in concentration can be used to find out the filtration velocity using this equation, where the dilution volume, the diameter of the borehole. So in this case, as I said, you have only one well, you inject the tracer there, then you monitor only in that well. That will get you the filtration velocity. Now coming to the flow direction, if you want to see, then you have many more wells. You have one injection well, and you have many more wells, because you do not know in which direction the groundwater flows. So you inject the activity here, you keep on sampling in all the other monitoring wells, and when the activity comes, you can find out the time elapsed and the distance. Divided by that, you will get the flow velocity using the multiple well technique. Now, if mainly as a hydrogeologist or a geotechnical engineer, you want to know what is the hydraulic conductivity of the formation. Many times lab experiments, because they are all small scale studies, but whereas this type of studies using Darcy's law, if you know the hydraulic gradient and the velocity which you calculated using this tracer injection, you can find out the hydraulic conductivity based on this type of studies. Now, coming to the source of salinity in groundwater, many of you are interested in salinity of groundwater. The moment you people say salinity of groundwater, everybody say it's seawater intrusion, but that is not the case, because salinity can come from seawater intrusion, and seawater intrusion, not only the present, right now the seawater intrusion take place, or in the past, because in the past sea might have transgressed into the land and that water is trapped. Isotopes can differentiate the seawater intrusion, whether it is present seawater intrusion or the past seawater intrusion. Seawater and this salinity can come from leaching of salts from the formation. From then it can come from, because of the evaporation also, salinity can come. It can come from the anthropogenic activity like fertilizer use, from salt pan activities. So many more anthropogenic activities also the source of salinity. Now, isotope can differentiate all these processes. See, for example, if you measure the oxygenating and electric conductivity of a water, this is a stable isotope if you use. If there is an evaporation, what happens? Isotopic changes, but electric conductivity will not change much. So it will fall in a line like this, parallel to the x-axis. In the case of leaching, what happens? The electric conductivity increases, salt content increases, but isotope will not change. The oxygenating will not change. So leaching samples normally fall here. And if there is a seawater intrusion, you have the pure groundwater if you have a sample, and if you have the seawater here, and draw a line between, and if this your samples are falling in between, then you can say it is a mixing. So all these process can be studied simply by collecting a sample and measure its isotopes. Now, coming to the seawater intrusion versus groundwater discharge, you all know about this coastal aquifer system. The seawater flows into the sea. Many times the seawater flows into the sea, and there is a interface, you all know, because the density of saline water is high, so the water intrude into the aquifer in a deeper horizon. If the hydraulic gradient in the shallow zone is very high, the groundwater flows into the sea. But if the hydraulic gradient is very less, the seawater intrude. So this dynamics can be studied using isotopes. Now, coming to estimation of submarine groundwater discharge. See, because see, this is a typical example of the coastal aquifers in India. We have the Western Ghats here, and we have the sea here. So we have a lot of rain in Kerala, Tamil Nadu, sorry, in Karnataka, all along the Western India. We have a lot of rain happening there. The aquifers are recharged, but in summer we have water problems also. So that means that a lot of water is going into the sea. So there is no estimation or how much water is going into the sea that can be estimated using isotopes. So, and also because many of the shallow
Dr. Noble? Dr. Noble?
Participants, kindly wait here for a few minutes. It seems like there is a loss of internet connectivity in Dr. Noble's side. So we'll get back to you in a few minutes.
Hello? Hello?
Hello, sir.
Am I audible?
Yes, sir, you are.
I am very sorry. I don't know. There is some problem with the internet. In between, it got cut. I continued to deliver my talk. I don't know. Nothing has come, or
No, the presentation has not come in the screen yet, sir. It's okay, sir. It's all right.
now what
Sir,
will we
you
do?
can, so you can share screen once again. I
Okay.
mean, from the start.
Okay. Yeah. Hmm. Hello?
Yeah, the presentation is there, sir. Now you can move on to the slideshow part.
So should I start from the very beginning, or what should I do now? Hello?
No, sir, you can
You
resume.
have now only 15 minutes.
Okay.
Only
So
15
nothing has come, or
only.
did you hear anything from?
Now the presentation is there, sir.
Okay.
You can resume your presentation from
From the
where you
very
stopped.
beginning, should I start from the
No.
very beginning, or
No, sir,
No.
you don't need to start over. You can
You
continue.
have only 15 minutes remaining, Dr. Noble. 15
okay?
minutes.
Okay, I am very sorry with because of the internet problem. So anyway, I will talk a bit on the some of the civil engineering applications. Uh, Coming to for finding the safety of dams. Uh, Isotopes can be used to find out the hydraulic connection between water body. That is, if there is a seepage in the dam, we can collect the sample from the seepage point as well as from the reservoir and see whether they are same or different, and what is the source of seepage, whether it's coming from the reservoir or from the groundwater, and identify the location of the seepage entry zones, and we can delineate the seepage path in the dam body. And also, if some grouting and other remedial measures are done, that can also be studied using isotopes. Also, we can examine the soundness of the bedrock, whether the rock is soft or hard, whether it can hold the water or not. Those things can also be studied. This is a study which we have carried out in Nagawadi Dam in Maharashtra, wherein it's an earthen dam, and after filling the gorge section, there was a few seepages seen in the downstream. So what we have done is to find out the seepage entry points. We have collected the water from the reservoir at different depths, and this is the isotopic variation of the reservoir water at different depths in the reservoir. So as we see, there is a higher value in the top, top 15 meters, and afterwards the isotopic values changes gradually. So by comparing the seepage water with the isotopic value of the reservoir, you can say whether it is coming from this depth or from the bottom. So that way, environmental isotopes can be used to find out the seepage entry zones. Now coming to seepage zones in the reservoir. Here we see there is a reservoir in Maharashtra again at Boda reservoir. There the reservoir could not hold the water for a long time. Because after the monsoon, the water empties from the reservoir. So they want to know the entry zones in this dam here in the reservoir. Where is the entry zones through which the water escapes into the subsurface? So we injected the radioisotope, which is adsorbable tracer, which adsorbs to the sediments. Once it is mixed in the water, it get absorbed into the sediments. So if there is a seepage point here, these tracer will get absorbed into the sediments, and by tracking on the bottom of the on the reservoir, we could find out the seepage entry zones in the reservoir. Now coming to seepage path in the in a reservoir, sorry, in a dam, in the body of the dam. Suppose there is some leakages and there are some cavities there. If we can inject some activity in the cavity and see whether in the downstream boreholes whether the activity is coming or not. So at the ender, if there are many more boreholes in the body of the dam, if you inject in one borehole and if it is coming from the other, we can see the vertical variation of activity at different places. There are some bore wells where you find at a particular depth the activity increases. So based on that, the seepage points can be identified. Now coming to some sedimentation rate studies which we have done in Vembanad Lake, which based on cesium-137 measurements. Cesium-137 is a fallout of the thermonuclear bomb test carried out in the atmosphere in 1960s and till 50s and 60s. So because of the bomb test, a lot of cesium-137 is a particle. Cesium is a solid particle. So it get dry deposited into the sediments and it get absorbed into the sediments. And when the sediment moves from the catchment to the lake, it get deposited. So by collecting a core from a lake or a lagoon, and slice it and measure the cesium-137 in that, you can find out the sedimentation rate, how it is. See, this is the sediment core. We have collected the 50 centimeter core, and this is a cesium activity there. And the maximum activity is found up to here around 25 centimeter, and that correspond to 1963 because of the fallout cesium-137. So the time elapsed can be found out, and the depth divided by that time lapse gives the sedimentation rate, and based on that the life expectancy of lake can be studied. In the case of Vembanad lagoon, we found 5.6 mm per year is the sedimentation rate, and same way the heavy metals in the sediments also measured, and this is used as a 1963 peak is used as a time marker, and the pollution before 1963 and after could be differentiated. The same studies again we did for Shastangota Lake in Kerala. Now, soil erosion in a catchment can be found out using cesium-137 again. This is the catchment with a different land use pattern. You have the forest region, you have cultivated land, and this is a reservoir. So the cesium, if you take the soil profile in the cesium in the forest region, which is undisturbed sediments, you have a profile something like this. And whereas in cultivated land where the sedimentation erosion takes place, the activity concentration reduces, but whereas where there is a deposition in the case of a reservoir, it increases. So based on the soil collected at different places, soil core collected at different places, you can estimate how much is the erosion. So soil erosion there. Now coming to the sediment transport in marine region, especially for the ship to come into the port, the navigational channels are made and they are continuously dredged. Now how these dredged sediments are deposited at some places, and we want to know whether the dredged sediments are coming back to the channel or it remains there. So because it has to be continuously dredged. So if you dump it at the far off place, then it is a costly affair. But if it is dumping close, it will come back to the channel. So these radio tracers can be some sediment glass powder can be made radioactive, and which is injected in the places, and we can monitor. This is the injection point where we injected, and we found that after some time the activity has come to the channel. So this type of studies also can be done. Now coming to the use of tracers in oil management. because we all know about the primary recovery of oil exploration in the petroleum industry, where under natural pressure, this is the oil field. Under natural pressure, the oil and the gas comes to the surface. In the secondary stage, where the pressure is less, normally what we do is there is an injection well here, and there is a set of monitoring wells. The production wells around it. So inject water in one of the well, and whatever the oil water mixture comes from the production well, that is used for the recovery of the oil. Now we want to know what is the residence time between the injection well and the production well, and what is the residual oil saturation present in it. All those things can be studied using injecting two tracers. One is a passive water tracer, and another is a oil tracer, that is carbon-14 in the form of methyl alcohol, which is injected. So this is a typical tracer curve we get. Based on the center of gravity, we get the time lapse between these two, and if you know the partition coefficient, the residual oil saturation in the injection well can be studied. And also it can be used to find out the preferential direction of oil movement, and residence time, fraction of injected water reaching the production well, and residual oil saturation can be calculated. So this is the last slide. If you permit, I can tell some of the applications, or we can have a question answer session. Thank you.
Please continue. Please continue.
Okay, because I'm coming to some of the previous slides, I can quickly see. See, for example, in the case of canals and mountain rivers, the flow rate can be calculated. See, even the flow rate up to 1,200 meter cube per second. That sort of, see, for example, a mountainous river. See here, the tracer is injected and then monitor. Here, the principle is that at one point you inject continuously the tracer into that with a constant flow rate, and you monitor the concentration of the tracer at the downstream side, and assuming that it is well mixed, using this mixing equation, you can calculate the discharge of the canal or a mountain river at the downstream without having any any flow rate measuring instrument. This is just by tracer concentration we can calculate that. Now coming to some of the previous talks which I have, I don't know whether you have listened to that. See, about the salinity of groundwater. See, the moment we say salinity, we all say that it is due to the seawater intrusion. But isotopes can differentiate the salinity because of the present day seawater, or seawater due to seawater intrusion in the past transgression of the sea, or it is you can differentiate between the leaching of the salts from the formation and by evaporation process, or through anthropogenic activities such as the salt pan activities or irrigation and things like using isotopes we can differentiate that. And the groundwater which is discharged into the sea, if there is no seawater intrusion, obviously there is a groundwater discharge taking place into the sea, that can be estimated using isotopes. And the groundwater velocities can be calculated, whether you inject the activity in one well and monitor in the same well, or you have a multiple wells, you inject other wells, you can calculate the groundwater velocities. Then this can be used to, isotopes can be used to find out the subsurface temperature, especially in the geothermal area. What is the recharge zone for these waters? What is the degree of interaction with the rock, and from where the temperature comes from? Mixing studied, and this is a study where isotopes help to identify the source of water. See, this is a study in iron ore mining area in Goa, because there was a public outcry that mining activities has polluted the groundwater there. So we have done a study here. We collected the mine water and we have collected the groundwater in the nearby region, and we have measured its isotopes. And this is the oxygenating versus deuterium plot. We found that the groundwaters are falling in the global material similar to the rainwater samples, whereas the mine water are falling here. So since they are different, that means that the mine water is not contributing to the groundwater. If the groundwater is mixed with the mine water, obviously this groundwater might have moved here and mixed with the it might have placed here. The mine water is not contributing to the groundwater. Now, this is a study which we have done to understand the dynamics of deep aquifers in the Barkile system in the South Kerala sedimentary basin. In the South Kerala sedimentary basin, that is extends from Kollam to Cochin. The deep groundwaters are used for drinking purpose, especially in the Alapi region. Isotopes help to understand what is the recharge source and history of the recharge, the interconnection between the shallow aquifers and the deeper aquifers, and the
This
mechanism
portion,
of
excuse me, Noble, this
yeah,
portion
yeah.
already you covered.
Okay, so this is all about. I don't know, because where I have where my connection went wrong. I think I have covered almost everything. So I just want to say that the isotopes can be used to find out any subsurface flow, especially the hydraulic problems connected, whether the connection between two water bodies or seepages in dams, reservoirs, whether the seepage is coming from the reservoir or it's coming from the groundwater. What is the by injecting tracers, we can find out the flow path in the dams, and those all interconnection, hydraulic interconnections can be studied. The groundwater discharge to the marine area can be studied. Lake dynamics can be studied. So seawater intrusions can be studied. All sort of subsurface problems can be studied using isotope. It's an independent field-oriented study rather than theoretical calculations and modeling studies. So this would corroborate, basically, if you can do some sort of tracer studies along with the lab studies and the modeling studies which you do routinely, so that your results can be more promising. You get more information from there, and it's a confirmatory check. And even in the case of nitrate pollution, if there is a pollution, see, nitrate, we say it is from the sewage or from the fertilizers. But whereas if you measure its isotope, N15 isotopes, we can differentiate whether it is coming from the septic tanks or from the animal waste or from the fertilizers. We can differentiate it. And what is the process, whether it is denitrification or nitrification process taking place, those things can all be found. I think I have covered almost everything. Only thing, I am very sorry that there was some problem with the connection in between, which I was not knowing. I was continuing my lecture here, slide by slide. I'm very sorry for that. Still, I hope I have conveyed the message that there is a technique available, a tracer technique available, which you can use to solve the subsurface problems. Thank you very much.
Thank you, Dr. Noble. Thank you for spending your precious time with us. It was very informative talk, and we were new to these isotope techniques. Okay, you could enlighten us with this special talk. Thank you so much for joining with us for this faculty development program.
Thank you very much for inviting me for this presentation. I am very extremely sorry that this is because of the internet issues. I could not present properly, but still, I hope that the main objective of this presentation is to make you aware that there is a technique available which can solve the problems related with the subsurface weather or in the dam studies, hydraulic studies. So there is a technique available. That's the main motto of this presentation, because this entire thing you cannot learn in a single presentation, but at the same time it gives an overview that there is a technique exists which can be used. There is a lot of scope for this, because especially environmental isotope, which anybody can start this type of work, because you can collect, you need to measure, procure an instrument for the measurement of isotopes, and you can collect sample and do the measurements, or you can use artificial tracers like dye tracers. So those things can be done. It can solve some of the basic field problems.
Dr. Noble, there is one question.
Yeah.
Okay. In the catchment area, which is
Okay.
flat, okay, I think
Okay.
that it may be there is no hydraulic gradient. In such a case, how
Okay.
can measure the tracer in downstream area? I don't know, somebody has posted this. If there is no
Okay.
hydraulic gradient,
Yeah.
there is no downstream.
Okay, that's a very interesting question. Now, first of all, I want to know, in a flat area, is there any groundwater flows or not? Normally, we all know if there is a hydraulic gradient, then only the flow takes place. But if there is no flow, then what happens? That again, you look for the geology. If it is a sedimentary basin and it is a flat area, obviously there is a vertical movement. Then you can use tracers to find out how much is the vertical movement of water joining the deeper aquifers. That can be studied. And if you want to study the horizontal flow, then you can do a tracer experiment and see whether the flow is really happening or not, whether you are getting appreciable velocity or not. Doing an experiment, we can find out whether it's an active area, whether the flow is taking place or there is no flow. That can be done.
Okay, thank you, Noble. There is only one question from the participants.
Yeah.
Thank you very much once again for spending your time with us. Okay.
Okay. Thank you so much. I am extremely sorry once again.
It's okay. No problem.
Okay.
You have covered everything.
Okay.
Whatever we have discussed earlier, everything you have covered. That's okay. Now to the participants, thank you very much for attending this session. Tomorrow we will have Dr. Shivakumar, who will be discussing about the drag forces in soil media. He is from University of Grenoble, France. We will see you all tomorrow at 6:45 p.m.
Thank you.
Thank you.
Thank you, sir. And for the participants, once again, for those who are listening through the YouTube live streaming, you can contact the organizing committee for the attendance form.
On behalf of Rajagiri School of Engineering and Technology, we express our sincere gratitude to the participants and the chief guest of this day for gracing this session. See you all tomorrow.
See you all tomorrow. Good night and stay safe. So we're keeping the platform there for 10 more minutes so that you can fill out the attendance sheet. Once again, good night and stay safe.